So the acronym to determine if your word problem follows suit with a binomial setting is BINS. The first question you're going to ask is the situation binary? Binary means two things can happen. Either what we would consider a success happens or a failure, and I'll explain more on that later. But when we start the homework next time, it'll just be, hey, read the situation and just determine if it's a binomial setting or not. If you determine that either one of two outcomes is going to happen, either a success or a failure, then you can check the B in the acronym BINS and move on to the I. I means, are the trials independent from one another? Now, you should know by now that that means the outcome of one event does not affect the next event. If that's true, you can check the I and you can move on. Sometimes it may even tell you explicitly these events are independent, which is nice. N represents the number of trials. That's going to be denoted by lowercase n in our formulas today, and you'll write that in just a second. But the number of trials is fixed in advance. All that means is they will tell you in the word problem, like, hey, you're going to flip a coin 50 times. They will tell you the number of trials in advance. If that is true, then you can check the N and move on to the S. S means, does every single event have the same probability? The same probability of success. And that's lowercase p that you'll see in our formulas today. And you'll write that in just a second. But lowercase p is the probability that you get a success. Let's say I want to know the probability that you flip heads. Heads would be the success, tails would be the failure. What's the probability that you flip head? 0.5 every single time. The same probability every single time you flip a coin. So S means, do we have the same probability of success on every single trial? And if you do, then you can check it, and then that just takes you through the BINS acronym so you know as a student, hey, this is a binary situation, so I can use all the binary formulas on the formula chart. What is a binomial random variable? Well, capital letter X. We've talked about discrete random variables. We've talked about continuous random variables. Binomial random variable is the number of successes in n trials. This represents the number of successes in n trials. That means you could look at a problem where you have no successes at all. Like I flip a coin 50 times. I'm looking for the amount of times I get heads, and I don't get any heads at all. And that'd be 0 successes. I could have 1 success, 2 success, etc., all the way up to all of the trials resulting in success, which would be n, because n is the number of trials we perform. And the next little part says, what are the parameters? That's a fancy way of saying, what are the variables we're going to be plugging into these formulas? And I just said a second ago, n is the number of trials. That will be given to you in the word problem. How many observations you're doing or how many trials you're performing, it'll tell you that. P, we mentioned up there at the top of the page, P is the probability of success on one trial. So if we're flipping a coin, the probability of a success, if we're calling heads a success, is 0.5. The most common mistake students make is they really don't recognize a binomial setting, so they don't know to use those formulas on the problem that they're staring at. And I think it's because they don't stop to check with the BINS acronym if the problem at hand is a binomial setting or not. So just write students. One of the most common mistakes is students not recognizing that using a binomial distribution is appropriate. So my hint to you is so that you can kind of stop and think about what kind of probability problem is sitting in front of you is if you were asked a probability about a count of something, if you are asked a probability about a number of things, a count of something happening, like the probability that you get, you flip 30 heads in 50 trials. That's another way of saying they're asking you for the number of successes. If you're asked that, try it as a binomial. Check your BINS acronym and try it as a binomial. I feel like that would actually be better at the end of your notes, just to kind of wrap it up and tell you, how are you supposed to recognize these problems? Okay, let's look at this first little part. I'm going to lead you up to where these formulas come from on your chart. That's your favorite part of the notes, right? Is figuring out how these formulas are derived. In many games involving dice, rolling a 6 is desirable, probably just because it's the highest number. The probability of rolling a 6 is 1/6. Now, you should know that without being told, but the probability of rolling a 6 is 1/6. If X is the number of 6s in 4 rolls of a fair die, then X is binomial. Number of trials, the number of rolls, is 4. The probability that you have a successful roll, in other words, you roll a 6, that's 1/6. Let me show you really quickly off to the side. If they hadn't told you the part that I just highlighted, if that part was completely missing, you would still have to recognize all of that was true. So they actually wouldn't tell you that. You would have to know, okay, I'm rolling a die, I'm either going to get a 6 or I'm not. So that's a success or a failure. So I could check the B. It's a binary situation. I'm either going to roll a 6 or I'm not. Independence. Okay, well, each roll is independent of the next one. They don't affect each other. So the I could check that for independence. I'm rolling the die 4 times, so the number of trials is 4. It's fixed in advance. If you look at the top of your page, that's what the N is. It's fixed in advance. And the probability of success does not change from roll to roll. I have a 1 in 6 chance of rolling a 6, so my probability of success is 1 out of 6 every single time I complete a trial. That's me just checking the BINS acronym off to the side if they hadn't told me the highlighted information. They literally said X is binomial, so you don't check for BINS if it tells you it's binomial. But I wanted to model that for you. So this says what's the probability that the number of successes is 0. That is the probability that I roll a die 4 times and I don't get any 6s at all. Let's call rolling a 6 a success. All right, rolling a 6 is a success. I'm just going to denote that with a capital S. That is not a 5. I made it as curly as I could. That is a success. So the probability of rolling a success is 1/6. We're going to say that anything else is a failure. Rolling a 1, a 2, a 3, a 4, or a 5. So not rolling a 6 is a failure. We're going to call that F. Well, the probability that you fail is what? 5 out of 6. Successes and failures are complements of each other, so the probabilities will always add to 1. That will help you out when we get to some of the scary looking formulas. So here the question is asking, what is the probability that I roll a die 4 times and I don't get any successes at all? No successes. That's the same thing as the probability that I fail, 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 fail. Well, these are independent of each other. I checked it in the BINS acronym. As a matter of fact, since it tells me it's binomial, automatically that means these trials are independent. So there's an old rule that says this: if you want to know the probability of 4 things happening and they're independent of each other, then you just multiply the probability of those each happening to each other. So I can multiply the probability that the first one is a failure times the probability that the next one is a fail times the next one is a fail times the next one is a fail. And we would write that as 5/6 to the 4th power, which would give us 0.482. Before you turn the page, make sure you understand what we just did. The probability of 0 successes implies 4 failures if you're rolling a die 4 times. So I end up writing the probability that we fail to the 4th power. All right, turn the page. What's the probability? Same problem. I roll a die 4 times and I get a success exactly 1 time. I roll a 6 exactly 1, so equals 1, exactly 1 of the 4 times. How many ways could this occur? Out to the side, here's what I mean. My very first roll could be a success, and then I fail, fail, fail. That's one of the ways this could happen. My first roll could be a fail, and then success, and then fail, fail. I could fail, fail, success, fail. And lastly, I could fail, 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 and then I finally get a success. There are 4 different ways, 4 ways in which getting 1 success of 4 trials could occur. That's going to become very important to us because there's a way we can shortcut this eventually where we don't have to go out to the side and make a list. So bear with me here. Let's map out the first thing that I wrote over here happening, where I get a success, fail, fail, fail. These are independent of each other, so I can just write the probability that I have a success on the first trial times the probability that I fail, and then fail, and then fail. And a short way to write that is I've got 1 success and 3 failures. So failure to the 3rd power. Okay. What about the second thing I wrote over here? Fail, success, fail, fail. That would be I fail, I succeed, I failed, I fail. Do you notice anything yet? Oh, it's the same thing. Well, I'm glad you noticed that because that's going to save us from having to write all of this. Yay! I do want us to just kind of finish our thoughts here though. If we went ahead and did the next one, don't worry, I'm not going to make you write it all. Fail, fail, success, fail. We would also end up getting the 1/6 times 5/6 to the 3rd. In other words, it doesn't really matter what position your success happens in. It's only going to happen once. You'll have 3 failures. So fail, 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 success would also be the same thing. Interesting. No matter what position your success is, we're just looking for one of those and 3 failures. So here's how you can sum it all up. The probability that you get exactly 1 success. Well, the same thing happened 4 different times. So 4 times the probability of a success happening times the probability of a failure happening 3 times. I'm going to go ahead and tell you that's 0.386 because I have all the faith in the world in you being able to type that into your calculator, but we're just trying to save a little bit of time here. Now listen really closely to what I call this 4 right here. Off to the side, when you figure out how many ways this can happen, that's called the coefficient. Coefficients go in front of things. So I'm going to circle back to that in a second. The coefficient here ended up being 4 because there were 4 different positions that success could have been in. Let's see if we can fast track it and figure out pretty quickly the probability that I get exactly 2 successes, exactly 3 successes, exactly 4 successes. We're going to start with 2. I need to know what that coefficient is going to be. Like, how many different ways could 2 successes happen? Make a list out to the side. I could get success, success, fail, fail. Success, fail, success, fail. If you want to go on your merry little way, go ahead. But stay organized. Success, fail, fail, success. Fail, success, success, fail. FS, FS. Or FFSS. That's kind of a pain in the butt. What if you were to accidentally forget one of those? It would ruin your whole problem. So keep that in mind. But we just discovered there are 6 different ways, 6 different positions that those successes could be in the 4 roles that I did. So that becomes the coefficient. The 6 now goes in front. Now think about this. This is really easy. In 8th period, I know you'll get it. How many successes was I looking for? 2. So the probability of a success, I'm going to raise that to the 2nd power. Because if I listed all of these out, I would want success times success, which would mean how many times will failure occur in 4 rolls? 2. Notice those exponents add up to 4. Those exponents add up to the number of trials. I'm rolling the die 4 times. If I get 2 successes, I'm going to get 2 failures. If you crunch those numbers in the calculator, you're going to get 0.116. So even less of a probability than we got up here. Okay, the probability that I get exactly 3 6s when I roll a die 4 times. Let's figure out how many times, how many different ways we could get 3 S's. S, 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 F. S, S, F, S. S, F, S, S. F, S, S, S. 4 ways. Now that wasn't that bad, but again, what if you accidentally forgot one of them? Like, how do you check yourself and make sure you got them all? I'll tell you in a little bit. So 4 is the coefficient. Now why is this one going to be any different than what we did right up here? 4 is in front. Why isn't it still going to be 1 out of 6 times 5 out of 6 to the 3rd? Yeah, this was just 1 success, so essentially it was raised to the 1st power. Here we want 3 successes, and we want 1 failure. See, the probability keeps shrinking because we're wanting more and more successes. And the probability of that happening gets lower and lower. What we're about to figure out here is, look how slim the chances are that you roll a die 4 times and all 4 of them are 6s. How many ways can that happen? 1 way. S, 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 S. So 1 times, that's your coefficient. We want all 4 to be successes. So the probability of a success to the 4th power, the probability that we fail, how many of those do we want? 0. Ooh, so does this whole thing just turn into 0 because 0 times anything is 0? No. That's right. And a lot of us, including me, sometimes forget that anything to the 0 power is not 0, it's 1. So no, this is not going to be 0. It's a very, very small probability, but it's not 0. It's not impossible for that to happen. So I'm finally there where I can show you the formula that's on the formula chart. It looks really scary, but it's not because you just did it like 4 different times. Okay, here's what you did 4 different times in a row. Believe it or not. You did all that. That's on your formula chart, so don't sweat it. You just have to know how to read it. You've never seen this notation before in your life in any other math classes, to my knowledge, because I've taught all maths up until here, and I don't teach this in any of my other math courses. You can get all this thing.
I'm gonna pass.
Just take this one.
Thank you.
See that like tall skinny parentheses with the N and then like a space and then an X on the bottom? What in the world does that even say?
That's the number number 10.
The top one is the number of trials. The top number is the number of trials. X represents, it is not a division, it's not divide. That's the number of successes. And I already told you, do you remember what P stands for in all of these formulas? The probability of success, specifically. Now I just have to tell you how to read this thing. And I'm going to show you that your calculator can do this for you. What this is how many different ways could this happen? You know how we figured out the 6 and the 4 and the 1 before, and I kept telling you, well, what happens if you mess up over here? So this is called the binomial coefficient. Because it goes in front. And it tells you how many different ways this many successes can happen out of this many trials. In the problem we're about to do, we're going to need, out of 10 trials, we want 4 successes. It would take forever to make a list of all of those. You're about to see how many that truly is. Your calculator, it's a combination. How many different combinations of 4? How many ways could I get 4 successes in 10 trials? So it's going to look like this in the calculator. I'm about to show you how to do that. 10, choose 4. If you will get your calculator ready. Type in 10. Hit math. And go over to the probability menu. And it's option 3, NCR. It's not a permutation, it's a combination. And then you have to type in the 4. So these old calculators, you have to type in the front number, and then that kind of cluster right there is like the C, and then the 4. And hit enter. Aren't you glad we didn't have to make a list? Because the list with all the different positions those successes could be in a string of 10 would be 210 items long on our list. Gross. The binomial coefficient is something your calculator can take care of. Let's see how we would use that in this next problem. I think these are kind of fun once you get the hang of them, but I'm gonna like that. In roulette, 18 of the 38 spaces on the wheel are black. You observe the next 10 spins of the wheel. What's the probability that exactly 4 of the spins land on black? Let's check and see if this is binomial. Really quickly, this shouldn't take more than just a couple seconds. Is this a binary situation where we're either going to get a success or a failure? What are we going to consider success? Spinning a black, because that's what it's asking me about. Okay, cool, so done. Are all of the spins independent of each other? Yeah, because what happens on one spin is not going to affect the next spin of the roulette wheel. Is the amount of trials predetermined? How many trials are we observing? 10. Is the success probability, the probability of success, the same every single time we spin? And what's the probability that we get a black every single time we spin? You guys are great. Fantastic. So guess what? This is a binomial setting. Well, no duh, it's in our notes. But that's how you would check. So here we go. We're allowed to now use that really scary formula that you highlighted right up there that says, all right, the probability, we want the probability of exactly 4 successes, 4 blacks. So that first little tower your binomial coefficient there, is 10 trials, 4 successes, which we just discovered a second ago. That gives us 210 right there. Times, look what the formula says, probability of success raised to the power of how many successes you want. So 18 out of 38 is the probability of success, and I want 4 successes. Let me show you a shortcut. Instead of writing 1 minus 18 out of 38, you guys, if 18 out of 38 are black, how many of the slots are not black? 20. So that 1 minus p is just the complement of success. Those fractions will always add up to be one whole. If I'm looking for 4 successes, how many failures would there be in 10 trials? 6 failures would happen. That's all this formula says. You don't even have to worry about typing all that into the calculator. Just trust me, because there's an even easier way we're going to look at in just a minute. But what you would get if you typed all that into the calculator is 0.225. That's the probability that we would get exactly 4 land on black 4 times out of 10 spins on the roulette wheel. Okay. Well, the next one is worded differently. What's the probability that at least 8 of the spins land on black? That's different than exactly 8. 8 or more, how do we write that with symbols? Good for you. So that means I'd have to add together the probability that we land on black 8 times to the probability that we land on black 9 times to the probability that we land on black 10 times. And here it really gets tedious. Get ready to write. I'm going to show you a shortcut. See how fast you can do this though. 10 trials, I want 8 successes. So I'm going to multiply that by the probability of success to the 8th power times the probability of failure to the 2nd power, because the exponents will always add up to be the number of trials. Plus 10 trials, 9 successes. So success probability to the 9th, fail probability to the 1st. Plus all 10 of my 10 spins land on black. Probability of success to the 10th power, probability of fail. I don't want any of failures. You won't ever have to sit there and do this. Because you turn the page, I'm going to show you how in one fell swoop, one little command in your calculator, it will do all of this work for you. You don't even have to worry about this whole binomial coefficient. So turn the page. How do you calculate binomial probabilities in, I should say in, the calculator? If you're dealing with a situation where it says like exactly 4 spins, you know it's an equals to setting, you're going to use binomial PDF. And then you'll just type in, remember what these stand for, the number of trials, the probability of success, and how many successes you want. So if you see an equal sign, or you write it in such a way that there is an equal sign based on the question, then you're going to use binomial PDF. Know that the P stands for probability, which means one single probability, an exact probability. I tell you all these things for a reason, it's so you don't have to end up memorizing extra stuff. Well, the only other thing your calculator knows how to do is a less than or equal to situation. seems kind of limited, because not every single inequality in the world is less than or equal to. So we'll learn how to handle that in a minute. But if it's an inequality symbol, you're going to do the command binomial CDF. So if you see any sort of inequality symbol whatsoever, then you're going to use CDF. This C stands for cumulative. That just means we're adding as we go. We've seen that word before. So inequalities denote that we're adding everything either that comes after that number or before that number. We're adding a bunch of stuff together, so cumulative. So inequalities, you're going to use binomial CDF. Well, these are the only two commands that your calculator knows. Either an exact or less than or equal to. These are the only two the calculator can do. So what do we do if it's a different symbol like this one down here? And we'll tackle that in just a second. Let's practice. I think you're going to like this. If X is the number of heads in 50 flips of a coin, find the following using your calculator. So what is that really asking me in words? What is P parentheses X equals 25 really asking me? The probability that I flip a coin 50 times and I get exactly 25 heads. That's what we're about to discover. So is that a PDF or a CDF? It's a PDF. It's an exact probability. So all we have to do, here's what you'd have to write on the AP exam. You'd have to write, hey, I'm going to use the binomial PDF function. And then you actually have to tell them, like you do with the lower equals, upper equals, all that business. Tell them how many trials are being performed, 50 flips. Tell them the probability of success on one trial. What's the probability that you get heads? Half. And we're looking for how many successes? Exactly 25 successes. Okay, as long as you write it out like that, then you can just go to your calculator and get the answer. Well, you're going to find these PDFs and CDFs in the same place you find normal CDFs, so second bars. You'll have to arrow down. There's A and B are your binomials. We're doing PDF this time, because it's an equal sign. How many trials are being performed? 50. What's the probability that you get a success on a trial? 0.5. And how many successes are we looking for? 25. How lovely. Enter, enter. There you go. 0.11. That's the probability that in 50 flips you get exactly 25 heads. All right, cool. Now I want to know, what does that mean in terms, in context? The probability that I flip 50 times and I get what? Less than or equal to 18. So I have to add together the probability that I get 18 with the probability that I get 17 and 16 and 15 and 14 and 13 all the way down to none. The calculator is going to do all of that for us with binomial CDF. 50 trials, probability of success is 0.5, and 18 flips. Behind the scenes, your calculator once again will be adding together the 18, the 17, the 16, the 15, the 14, the 13, etc. Second bars, binomial CDF, 50 trials, success of one trial, or excuse me, probability of one success, and 18 and less than that. 0.03. Cool. Any idea how we're supposed to do this one? It is definitely going to be CDF in there somewhere because it has an inequality. What'd you say? Yeah, what do you mean complement? Can you kind of walk us through your thought process? What's the complement of a number being greater than or equal to 30? If it's not greater than or equal to 30, it has to be what? Less than 30. So if you're like, wait a minute, what just happened here? Write it out in words. What is the complement of? What is the complement of greater than or equal to? Less than. Your calculator can only handle the less than inputs. It doesn't compute the greater than. So you've got to put it in terms of less than. Does that make sense? Put it in terms of. Well, you can do that by just writing the complement of this is less than. So the probability that I get 30 or more heads is the same thing as 1 minus the probability that I get less than 30 heads. So how would we type that in? We would type in 1 minus binom CDF. N is 50 trials. P is still 0.5, but here's where you have to pause for just a second. What are you going to put for number of trials? Yeah, you can't put 30 because you just said less than 30, so put 29. Let's do this. Type in your 1 minus first before you forget, because I always forget unless I type it in. What'd you say? So we discovered last period that putting a 20 right there works. Yes, because 20 plus 30 is 50. So that will work. It'll give you the same exact answer. Well, the way that I learned it was, as long as you're putting a number, the iteration that's just less than 30, so 29 successes happening, that would be the 29, 28, 27, 26, which is the complement of 30, 31, 32, 33, all the way up to 50. So put it in terms of less than, and if you put less than 30, make sure that the number of trials right here is 1 less than that. So 1 minus binom CDF 50.529, and you get 0.10. Is it okay to use these, like this notation on the AP exam? Yes, or I wouldn't have wasted your time by telling you that. But as long as you clearly state the number of trials, the probability of success, how many successes you want, and the direction. That means, like, use a probability statement with a symbol in it. Using a probability statement. When in doubt, just do things the way that I model them for you in the notes, okay? There are no shortcuts, or I would definitely be showing you those at this point, I promise. Especially in chapter 6. We're going to skip the next part, the next little part that says to graph a probability distribution, because I don't think we need it to really gain the knowledge that we need from this. So go right down to the bottom of the page. How can you calculate the mean and standard deviation of a binomial distribution? Finally, we're to something easy. Check this out. If you want to know the mean of a binomial distribution, on your formula chart, it literally says binomial distribution. To find the mean, you multiply the number of trials by the probability of success. That is it. That's the whole formula right there. Yay. You want to find the standard deviation once you've checked with bins that you're dealing with a binomial setting. You know for sure it's binomial. And you want the standard deviation. The formula is really easy. The square root of the number of trials times the probability of success times the probability of fail. Probability of success times probability of fail. We're going to use that on the next page. Finally, to something that's easy for those of us that just like to plug in formulas. Any questions so far? Turn the page. I think for us, it's the interpret piece that's going to trip us up. But calculate and interpret the mean and standard deviation of the number of sixes and 4 rolls of a die. We know that this is a binomial setting. If you want to know the average, the mean, in a binomial setting, do n times p. How many trials are we performing? 4 rolls. What's the probability of success that you get a 6? 1/6. That is all. You'll get 2/3 or 0.67. I'm not afraid that you'll, not be able to plug into that simple formula. I'm afraid that you may not understand what that means. So we're going to write a sentence, okay? Probability is the phrase in many, many trials or whatever. Well, we're not just talking about out of many, many rolls, but we're talking about out of many, many sets of 4 rolls. In many, many sets of 4 rolls. The mean, I'm going to write it the same way we wrote it in the other classes. The mean number of sixes, in other words, the average number of successes is about 0.67. That's interpreting what the mean of a binomial distribution is. So if this was a multiple choice question, be sure that it's got the phrase many, many. Be sure that it's talking about in many sets of 4 trials. Let's try standard deviation. That's the square root of the number of successes, the number of trials times the probability of success times the probability of fail. Now, if you really are thinking, this is 0.67, if you want to shortcut it, but I'm not going to. 4 trials, probability of success is 1/6, probability of fail is 5/6, because those will always add up to 1 whole. And you're going to get 0.745. Now, what the heck does that mean? And you know that writing standard deviation interpretation is kind of a beast, so here we go. In many, many sets of 4 rolls, the number of sixes will typically vary kind of like saying the number of successes will typically vary from the mean by about 0.745. Typically vary from the mean. That is the meaning of standard deviation. The number of sixes. Let me double check and make sure that's right. The number of sixes will typically be, yeah. I know that it's weird to say that the number of sixes you're going to roll is 0.745, but we're talking about in the long run.
Oh, does it mean it's already calculated?
Yes. Correct. Okay. Well, these questions are good because it checks me on my stuff. And then there's another little thing I gotta tell you. Don't you love it? When is it okay to use a binomial distribution when you see the phrase like sampling without replacement, or you're not putting something back. Like there's a bag of marbles and you pull one out and you see what color it is. Well, if you don't put that back, what's the problem with that? Then the next event is not independent, because what happened when you pulled the first marble out affects the next thing. So why would we be able to use binomial distribution stuff with that? So I'm going to tell you why. Okay, first things first, it's an issue because the phrase without replacement violates the independent in the acronym BINS. So you might at first glance think you're reading a word problem, they're not going to replace it, they're going to do another trial, and you might think, oh no, this isn't binomial. Must be something different. I must work this problem with a different formula. But that's really not a big deal as long as your sample size is small relative to the population. Not a big deal, like it's okay when sample size is small relative to the population. What does that mean? Like, what's the threshold? And it's 10%. It's called the 10% condition. 10% condition says this. If your sample size is less than or equal to 10% of the population, then you can use binomial distribution. If your sample is less than or equal to 10% of the population, then you're A-OK to go ahead and follow the binomial distribution formulas. And we're going to see that 10% condition show up pretty much the whole spring semester. All right, let's tie it all together with this one last problem that may take us the next 9 minutes to complete. According to a study, who comes up with this stuff? It's so weird. Most people are kissing the right way. That is, the majority of couples tilt their heads to the right when kissing. In a study, a researcher observed a random sample of 124 kissing couples and found that 83% of the couples tilted their heads to the right. I tried it with my husband. We do tend to just tilt our head to the right. I know, right? That's why I giggled. I thought of him like with binoculars. But seriously, like if you look at the little like people getting married in their like first kiss, watch, they tilt to the right. It's just a thing people do. So hopefully they got their consent to observe them kissing. But here's what happened. Out of 124 couples, 83% of the 83 of the couples tilted to the right. Well, we want to see what's the probability of that many couples or more tilting to the right, because then we'll be able to answer the actual question: is this convincing evidence that couples really do tend to tilt their head to the right when they kiss? So we're going to take what happened in this observation, and we're going to see, was that just like a lucky occurrence? What's the probability of that happening? All right. So let's check for the 10% condition. So you can see how that works. Because sometimes it's just implied. How many couples were in the sample size? 124 couples. Now, is that less than 10% of all couples? The population of all couples? Yeah. Are there more than 1,240 couples in the U.S., I guess? Yeah. Is less than 10% of all couples. So we just kind of double check. The 10% rule is good. Now that's really unnecessary because we didn't sample without replacement, whatever. Bins, we need to check that really quickly. Is this binary? Can we say success or failure? What is going to be success? Tilting your head to the right being kissed. Are each couple's head tilts independent of the next couple's head tilts? Let's hope so. Are the number of trials being performed predetermined? How many trials or observations were there? Okay. Is the probability that a person tilts their head to the right the same every single time? Yes, don't overthink it. It's not 83. It's not 0.83. It's 0.5. Yeah, you're either going to tilt to the left or you tilt to the right. Then that's just weird. That's just weird and nobody wants to kiss you, okay? Okay. Alright, I'm moving on. Give a room full of teenagers a question about kissing. I want to know the probability that that same result happens again, that either 83 or even more than that couples, or 83 successes, if you will, out of 124. So remember, your calculator can handle this, but for the greater than, we have to do the complement of that, which is the probability, 1 minus the probability that less than 83 couples tilt their heads to the right. That's 1 minus, is this binomial PDF or CDF? CDF, what is in? 124. What's P? 0.5. Do you remember how we handle the X part? 82, because it's less than 83. Grab your calculator. 1 minus binom CDF 124.5, 82. We get this weird answer. I thought probabilities couldn't be more than 1. Why am I getting 1.01? Oh yeah, because if you're looking at the whole thing, you see this e to the negative 4 power? That's your calculator telling you scientific notation. That's 1.02 times 10 to the negative 4th power. I would expect that each and every one of you sitting in AP Stats would know that's the same thing as moving your decimal 4 places to the left. Is that like a big chances of that happening by chance alone? No. So here we go. We've just got a couple minutes left. We've got to write a sentence to answer the question. Is this convincing evidence that couples really do prefer to tilt their heads to the right? And you might be thinking, no. Well, because getting 83 or more couples out of 124 who tilt to the right is unlikely to happen by chance alone. How do I know it's unlikely to happen by chance alone? Yep. We got a really small probability of that happening by chance alone, which means it wasn't just a lucky thing that happened. So there is convincing evidence. And the math backs it up for us. There is convincing evidence that couples tend to tilt to the right. That's all I'm going to write. Couples tend to tilt to the right when kissing. Whew. We are done for the day.